So I'm going to talk about retracing some of what Luis Davidovich said before. I'm going to speak about the fact that information is quantum. That is, these discoveries in physics have taught us that what we thought information was not complete and accurate. And up until about, I think I'm too loud. Am I too loud? No, okay, I will just, up until about 20 or 30 years ago, quantum mechanics was thought to be about physics. But now, at the same time, an information revolution was going on, and we now understand that it's the right way to understand information itself. So let's say, what is information? Well, we all know what information is because we're in the middle of an information revolution. In fact, the words for information come from experience, so like counting. A digit is a finger or a toe. And these ideas that you can think of information separate from the carriers of information were crystallized in the mid-20th century, and now they give us the world that we're living in. Everybody has several computers on their body. But it is known now that this idea of information was too narrow. There were things that physicists knew that Professor Davidovich just showed you that were discovered even earlier, but it turned out they had not only to do with physics and chemistry and light and matter, but they also have to do with information in a central way that should not have been left out. And the difference is that the information carriers had been viewed by the people who designed computers and all of the gadgets you use as things that have states that are reliably distinguishable and obey laws that actual real physical things don't behave that way. As you saw, quantum systems behave a little differently, and this difference can be put to good use. But unfortunately, for most of the 20th century, information theorists were aware of this difference, but they mainly thought of this uncertainty principle that meant that quantum things behaved less reliably. So they developed the theory of information processing based on this classical idealization, which worked very well, and it treated quantum effects just as a nuisance or a source of noise. But it was later realized that this nuisance can be put to good use, and now effects that you can do with quantum information that you couldn't do easily or you couldn't do at all with the kind of information we're all used to. So what's the difference? I don't have to explain classical information to you because you all understand what information is and how you use it in everyday life. But what is quantum information, and how do you explain it to somebody at a dinner party where if you start drawing equations, they just go to a different table? So I've put a lot of effort into thinking about that. And ordinary information, like the information in a book, you can copy it. Maybe it's against the law to copy it, but it's not physically impossible to copy it. We'll talk about things that you're possible to copy, but it's illegal a little later. But it's not disturbed by reading. You read a book, somebody else can read the book. But quantum information, what is that like? I can tell you mathematically, but first I want to give you a metaphor. Quantum information is like the information in a dream. When you have a dream and then you want to tell somebody about it, even the act of trying to describe your dream to somebody else changes the dream. So you don't remember the dream anymore, you only remember what you said about it. And you can't prove to somebody else what you dreamed or give them a copy of your dream. Now, quantum information is really like that kind of information. But unlike dreams, despite the efforts of Sigmund Freud, dreams don't follow well-established laws, but quantum information does. Quantum information can be carried from one place to another. Two streams of quantum information can interact, and you can even have a thing called a quantum computer. And you can use that to solve problems in sort of the way, I just thought of this, I thought of this metaphor last night while I was asleep. So to think of what a quantum computer does, it's like a person who has a problem that they can't solve, some kind of mathematical problem, and they go to bed, and they wake up in the next morning and they figured out the solution. And yet if they'd stayed up all night drinking coffee, they wouldn't have been able to think the solution. So I mean, that's clearly a metaphor, but there are things in an entirely exact way where if the process goes on with this dreamy kind of information, it can lead to a result that can be shared with everybody, but you couldn't have gotten from here to there that quickly without this dream process. So now I'm going to become much more rigorous. If you had to explain quantum theory in a single, I won't say this is a single sentence, it's just about, yeah, it is a single sentence. Between everything in nature, every physical system has some number of reliably distinguishable states. 2, 3, 4, or maybe billions, but some number. And between any two reliably distinguishable states, there are other states that are in principle not reliably distinguishable from either one of those. And the example that you saw just now was the difference between a vertically polarized photon and a horizontally polarized photon. They can be reliably distinguished, but if I give you one diagonally polarized photon and you try to ask whether it's vertical or horizontal, you'll get a random answer and you only get partial information. In other words, a diagonal photon sometimes behaves like a horizontal and sometimes behaves like a vertical. These two states, because they are not perpendicular, in principle imperfectly distinguishable. So quantum theory is the theory of imperfectly distinguishable information that follows a certain law. Now, this imperfectly distinguishability isn't just a fuzziness, it's that all states of a system behave like directions in space, not ordinary three-dimensional space, but a space that has as many dimensions as the maximum number of reliably distinguishable states. So in the simplest case, that's 2. Photons have 2 reliably distinguishable states. Any 2 perpendicular directions are reliably distinguishable. Any 2 non-perpendicular directions are not reliably distinguishable. Now, this doesn't look like it does very much for you, but if you have more and more photons, you get exponentially many reliably distinguishable states. For example, if I have 2 photons, they can both be horizontal, both vertical, the first one horizontal, the second one vertical, so that gives you 4 states. And the states of 2 photons can move around in a space of 4 dimensions, which is hard to talk about at a dinner party. And a space of 3 photons can move around in 8 dimensions. So this funny kind of exactly describable, imperfect, distinguishable corresponds to the ability to rotate in a space of a very vast number of dimensions. But in the end, when you want to ask a question about it, it has to describe to be an ordinary classical bit. So now I'll go on and get a little less technical. So here's the example that you saw already of polarized photons. Here we have this. I can see it and you can see it, but I can't point to it for you. So the horizontal photons can be distinguished from vertical ones, but the diagonal ones behave randomly if you try to ask them whether they're horizontal or vertical. But if you tilt your apparatus to 45 degrees, you can distinguish the diagonal ones from each other, but then you can't distinguish the vertical from horizontal. So there's in principle no way to distinguish all 4 kinds. And this is a feature that we make use of in quantum money, which was discovered about 1970 by my colleague Stephen Wiesner. So here's quantum money. You know, I don't know if you have ever seen a banknote which is printed on it, it says, if you copy this banknote and we catch you, we'll lock you up in jail for 6 years, something like that. This one, if you go to reading Latin at the bottom, it says, I shall not be duplicated. So it's physically impossible to copy this money because it has 20 polarized photons of those four kinds in perfectly reflective mirror boxes, and they were installed there by the bank, and when the bank gets it again, it looks at the first one and says, is it diagonal to the left? Yep. Second one, is it vertical? Yep. Third one, is it diagonal to the right? It checks them all. But if you're a counterfeiter, you're going to spoil some of them by trying to figure out what they are, and they'll catch you and lock you up for 6 years. So this is not very practical because you can't store these photons for more than a second or so, and the equipment to store them would be about as big as a car and expensive, and it'd only be good in places with very rapid inflation because the money would decay so quickly. But the same use, photons are very good for transmitting information as opposed to storing it. And this is about 1989, some colleagues of mine and I, like Gilles Brassard and I and our students at IBM and the University of Montreal built this thing, which used the same principle to transmit secret information over a distance this great, with the assurance that if anybody listened to it in the middle, the eavesdropping would disturb the information and they would get caught at their eavesdropping. So this is a practical use that you heard about from Louis before. Well, we also spoke about entanglement. Most states of a composite system are entangled, including these states that you use in the middle of a quantum computation. And this allows two particles to be in a perfectly definite state, even though each one separately is random. This is just an idea that it makes no sense, but it's the way the world works and you have to get used to it. Now, I was around in San Francisco in 1967, where there were a lot of people that believed they were perfectly in tune with each other, even though they had no opinion about anything. But they weren't very good at mathematics. So they believed that if you had enough LSD, everybody could be in tune with everybody else. But entanglement doesn't behave that way. It's monogamous. If two systems are perfectly entangled with each other, then they cannot be entangled with anything else. So this grows out of the mathematics and gives some of these very interesting and uniquely and useful properties. So it's ubiquitous, but as Louis said, it wasn't discovered before the 20th century because of decoherence. That is, a system that interacts with its environment becomes entangled with the environment, and when you lose track of the environment, the system loses its quantum magic, it loses its flavor. It just behaves like ordinary classical randomness. So in order to put this to use in a quantum computer, you need to protect the quantum information, which I've colored blue, these entangled, delicate states, from leaking out into the environment or anything from the environment leaking in. It's very hard to do, and you could say that if there's any leakage between the quantum computer and the environment, it's like the person is in the middle of their dream and they don't have time to finish it before they get awakened and the dream collapses. To be a little bit less figurative, a quantum computer cannot be perfectly isolated from its environment, but the same tricks that you use in a classical computer to correct errors, the same kind of tricks can be used to protect a quantum computer from errors. And this is an example of a quantum error correcting code, one that was simultaneously discovered a couple of places. One of them was at IBM, where if you take one quantum bit, you can entangle it with 4 others, and the resulting 5-bit combination is as safe, because if you spoil any one of the bits, you can decode it and get back the exact undisturbed original, and all of the damage goes into the garbage. And you can carry that, generalize that, and even correct errors that occur during the error correction process. And this is where the bulk of the work in the software of quantum computers is going. And as you saw, there are many approaches in the hardware, and the combination of better hardware that's intrinsically more reliable and better software for correcting these errors is likely to lead to a useful quantum computer, but it's going to be a lot of work and take a lot of time. So we say, well, what about this? We were having Moore's Law is coming to an end. They thought Moore's Law was going to come to an end in 2012. It's still going, but it's kind of tapering off now. So people always want to know, will quantum computers allow us to get around the problem that we can't keep increasing the speed of computers forever? And the answer is no. Well, it can be very useful, but in fact, when you study the difficulty of computational problems, there are some that are easy, like the blue ones at the bottom, like multiplication, that's easy for a classical computer. There are some that is easy for a quantum computer, but hard for a classical computer. And a couple of the more famous ones is factoring large numbers. I gave you an example on an earlier slide. Or simulating the physics of many body systems, which is important in material science and chemistry and you might say in biochemistry. And then there are some problems that we have every reason to expect are not really any easier for a quantum computer than a classical computer. Problems like the traveling salesman problem. So we have a new kind of computation, a new kind of data processing that will do things, some things that were hard before and make them easier, but there are going to be other things that are hard and will stay hard as far as we know. Thank you.